Morning, everybody.
Morning.
Good morning.
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 Recording in progress.
Well, I think we're approaching critical mass. Tim, you're scheduled to give a talk today. Are you ready to share your screen and start?
Yeah, my student Sa is going to give the presentation, I believe. So Sa,
Yes.
so I have, yeah, good. Sa, I have Sa and Bo, both are graduate students, and then postdoc Lu Ling working on this project. So I think Sa has been appointed to give the presentation. I did we did discuss part of it last week. I had to say that we really don't understand the data. There's some really interesting data you will see, but we don't have a full understanding. And so it's my hope that through this presentation we'll get a lot of good feedbacks and hopefully enlist some interest in the theory groups or other collaborations to push this project forward. All right, Sa, this is all yours.
Thank you. Hello, everyone. So today I'll be the representative to present our spectroelectrochemistry study of N2200. Let me get the data point. Okay. So some of this work is done by our graduate student Bo and also our postdoc Lu. So first of all, let's okay. First of all, I'll briefly introduce the goal of this project. So the first goal of this project is to achieve in situ probe of the monopolar and bipolar formation with different spectroscopic technique. For example, UV-Vis and also vibrational techniques such as Raman and APR-IR. And once this goal can be fully achieved, we understand all the information, then we can further extend this to time resolved study. So we can probe the evolution of monopolar and bipolar formation via time resolved absorption and also time resolved Raman and IR. So today, I will cover two aspects. The first project will be the spectroscopic electrochemistry study of N2200 using these three different techniques in both aqueous and non-aqueous conditions. And for the second aspect is also an interesting topic. We tried to use Raman as the vibrational probe of energetics at a N2200 gold aqueous electrolyte, this kind of configuration. To begin with, let's first have a brief introduction of the polymer N2200. So it also has a name of poly NDI2OD-T2 unit. So it contains this naphthalene diimide backbone as the acceptor unit, and also it has the electron donor unit consisting of bithiophenol. And this is first synthesized back in 2009, and it's an N-type or acceptor type semiconducting polymer reported with high mobility. However, the previous DFT calculation indicates that there is a large distortional angle between the NDI2OD unit and T2 unit, which partially hinders the charge delocalization along this donor acceptor backbone. And as a result, the polaron they predicted that the polyron is mainly localized on the NDI-2OD unit with limited interaction between these two, the T2 and NDI-2OD unit because of the large torsional angle. So far, here is this the current understanding of the polyron confinement in this polymer, and I believe the charge transport mechanism of N2200 and also the molecular structure of polyron has not been fully understood. So we should dig more into that. So here I'm gonna show a case of spectroscopic study under chemical doping, N-dope of N2200. So they use differently substituted benzyimidazole dopant to dope the N2200, and they use FTIR and also Raman, I will show later, to study the doping effect. So here shows a stacked FTIR spectra. On the top is the spectra for the dopant itself, and the bottom is the spectra for pristine N2200 itself. And IMR over here stands for the molecular ratio between dopant and N2200. So we can look at the IMR equals 1, which has the largest doping effect. So there are several IR feature change was observed upon doping. Firstly, the carbonyl stretching and also CC stretching of pristine N2200 disappear upon doping. And meanwhile, there are new features which is denoted by this asterisk mark, which shows 4 new spectra feature appears. Meanwhile, and they believe this is related to the polyron formation. And meanwhile, they also see the increasing absorption of these 2 peaks, because these 2 peaks already have bands appears in the pristine case, but the absorption increasing after doping. So in summary, they basically see vanish of some of the peak from neutral N2200, new peaks related to polyron, and also increasing absorption of existing peaks. They further did DFT calculation to mimic or to predict what could be the polyron structure. So on the top panel shows the N2200 peak and also the doped IR spectrum. And their DFT calculation predicts pretty well of the N2200 itself, and also they predicts if the polyron is localized as the radical I9, this red spectra will be the IR spectra, and it also aligns pretty well with their experimental spectra. So they predict that the polyron is actually localized on NDI-2OD unit as the radical I9. They further did the excitation wavelengths dependent Raman spectra. They use 4 different wavelengths to excite to create the resonance or pre-resonance state of the Raman spectra of N2200. So upon 1064 nanometer excitation, where they believe it is pre-resonance with the pi to pi star transition from the T2 unit, if we compare the undoped and doped spectra, we can see minimal IR feature change, and they believe it verifies the limited interaction between T2 and the localized polyron on the NDI unit. And then upon 515 nanometer excitation, where the polyron is actually resonant with these wavelengths, they similar to what they observe in the IR spectra, they see new features appear, and also they see the CO and CC stretch vanish. So from their vibrational spectroscopy study and also the DFT calculation, they believe the polyron formed by the chemical doping is actually in the state of radical I9 localized on the NDI N2200 unit. And T2 unit is not involved in the doping because of the large torsional angle limits the interaction. Meanwhile, they also learned something or hypothesized something else from the DFT calculation. So the fact that their radical I9 simulation from DFT calculation aligns with what they observed, they basically excludes the mechanism of hydride transfer from the dopants to the NDI-12D unit. And because they see the confinement of polyron just localized on the NDI-12D unit, they strengthen the intermolecular or interchain charge transport channel instead of the intrachain polyron diffusion. And for this mechanism, they believe there could be two possibilities happening. So there could be two interchain I9 radical I9 can form one di-I9 and produce another neutral N2200. Or there could be electron transport between the di-I9 and radical I9. So so far it is the spectroscopic understanding of chemical doping of N2200. And I'm gonna show you a spectroscopic study of electrochemical doping of N2200. So here shows the typical absorption spectra of neutral N2200. There are two major peaks at 390 and 714. And if so they in this experiment they use the gold electrode as the substrate, and the experiment is done in single nitrile. So when they scan from 0 to negative 1.2 volts, they can see two reduction peak. And to better study what are assigned to these two reduction peaks, they did the potential dependent absorption spectral measurement. So here shows the difference absorption absorbance spectrum. Once the first reduction happens, they saw decrease in the original peak of N2200, and they see growth in 490 and 860 nanometer peak growing. And in the second reduction peak area, they saw the decrease in these two previously growing peak, and with a blue shifted shoulder for both peak. So to better understand this data, they conducted the EPR measurement and compared them along with the UV and current data. So so the top two panel, it shows the first reduction process. So basically they peak the two growing absorption at 490 and 858. We can actually just look at this spectra, for example. So when current going grows up, where the first reduction happens, we can see that the absorption grows concurrent with the spin grows from 0 to 1. So they believe that this first reduction peak, since the EPR signal has the same trend with the increasing absorption, they think is the evidence of formation of radical I9 at the first reduction. For second reduction, they saw increasing blue shifted absorption. Meanwhile, they saw a decrease spin to 0.2. So the minimum EPR tells them basically it is the formation of di-I9 for the second reduction. So this is current understanding of the spectroelectrochemical doping of N2200. And I summarize the electronic transition properties for neutral and polyron bipolyron peaks. So we also did a similar experiment, but the first experiment I will show is done in water. So the solution is 0.1 molar KCl, and the working electrode is N2200 on FTO. The reference in water solution is the silver chloride electrode, and the counter electrode is just platinum wire. So if we look at the current data, we can see that during the cathode scan, there is a reduction peak at around negative 0.9 volts. And this is the real-time CV that we captured during the potential dependence absorption spectra measurement. And from the absorption spectra, we can already see there are some absorption feature change. And if we look at the difference absorbance spectra, we can see that we basically captured the similar thing. We saw after negative 0.9 volts, there are two peak growing, which is the peak that they assigned to the monopolar peak. And we also see the decrease of neutral N2200 peak, which can also be seen by the potential dependence of absorbance figure over here. So with that, we move to the vibrational spectroscopic measurement of similar sample, but this time we use N2200 on ITO, and we just keep other conditions the same. So from 0 to we scan the N2200 from 0 to negative 1.5. We can see there are two reduction peak with a 0.4 potential difference. And to the right is the stacked Raman spectra during the cathode scan from 0 to negative 1.5, and then back scan to 0 volts. We can already see some new features occur during the first reduction after negative 1.1 volts. And if we take a closer look at the spectra, I just chose three regions which have the obvious new feature appear. So for example, we observed two new features appear. The first one is at 1346. We can see that after negative 1 volt-ish, there is a growth in this peak, and then continued with the decrease. And we also saw a new feature over here at 1124. And similar to what previous literature saw from the IR and IR spectra, we also saw for existing band, there is actually a increasing in the Raman intensity for both of these two peaks. So this is what we observed in terms of Raman amplitude or intensity. And meanwhile, we can also saw the neutral N2200 related peak has a decrease. We will see this trend clearly in a bit. And meanwhile, we can also see a frequency change in the Raman spectra under or upon Polaron formation. For example, the carbonyl bond over here shows a constant frequency, and then after the first reduction happens, there is a redshift of the frequency, and then a recover after that. So we basically saw the band area change as a function of potential, and also frequency change as a function of potential. And I summarized basically all the peak that we observed from Raman and group them by different trends. If we first look at the band area, we can see clearly there are two groups of peaks. One shows a plateau Raman intensity, and after the first reduction, the Raman intensity decrease and then recover when the second reduction happens. And the other group of peak has the opposite trend. Meanwhile, we can also see for this group of peak, they also have a constant frequency and then a redshift of frequency and then recover during the first reduction and second reduction. And we think this is really interesting and we can dig more into it. So here I just mark the peak which have redshift by the red rectangular and blue shift with the other. So if we think more about this trend, for example, for the first reduction, what is happening as predicted by previous literature, there is a formation of the radical ion of N2200. So basically the neutral N2200 experience a 1 electron reduction to form the radical ion. So it's pretty natural to think that the neutral N2200 intensity will decrease. Meanwhile, the polaron-related peak will increase. And this is sort of what we saw here. So we think this group of peak is related to the neutral N2200 with decreasing intensity when the monopolaron appears. And meanwhile, this 4 peaks should be related to the monopolaron, which is the radical ion with the increasing peak intensity with more negative applied potential. But things get really complicated when it comes to the second reduction. So from also predicted from previous experiments, they think the second reduction is due to the formation of dianion. And if we think of the two possibilities of the reduction, the first one could be the radical ion get 1 electron reduction and form the dianion, or the neutral N2200 goes through 2 electron reduction to form dianion. But what we see from Raman is that the neutral N2200 Raman intensity actually increase or recover. Meanwhile, the polaron related peak or the polaron is consumed. Neither of this can explain the recovery of neutral N2200 peaks.
Hey,
So
I have a question.
Yeah. Mm-hmm.
Is it possible, and maybe this is good for everybody else, is it possible to have a disproportionation where you have a polaron and a polaron that goes to a dianion and a neutral?
Sorry, I didn't quite can you
Okay,
say
yeah.
that?
So a disproportionation reaction. So you have a radical anion plus a radical anion goes to a dianion plus a neutral.
Yeah, I'm about to propose this here.
Okay.
So
okay. Oh, right.
yeah.
Okay. Sorry. I jumped in before I think your slide flipped. I'm sorry.
Yeah, sorry. So so this is also what the previous literature proposed for the interchain hopping mechanism. And I think yes, so I think for now only this mechanism can sort of explain why the neutral N2200 intensity can recover. But I still think it's not rigorous, but this is what I can think of now.
I have a question. So this is, you assume that the dianion has absolutely different vibrational spectra from neutral, but is this proved?
Is not. That's a good point.
I guess
Yeah, I
don't know,
can't.
right? We are assuming there might be some difference. So this is where I think some computational help could be
Yes.
could be very useful here. My intuition would say there got to be some differences.
Because the electron density change.
Yeah.
Yes. Okay. I'll move forward and then
Can I just sorry. For those people who compute, who calculate this type of things, that means Chair and Jean-Luc, people, have you, there must be some literature on that already, right? Whether dianion and you know, have how big a difference is the vibrational spectrum of the neutral and the dianion? Is that known? And maybe we could look at some of this literature to give us some guidance on that.
I know that we have a paper with a Japanese group where we would, Jun Takeya's group, where we were doping N2200 by a variety of methods. And I've got it in front of me right now, and there's simulated anion and dianion spectra that I think must have come from DFT. I'm not quite sure. I'd have to read the details and remind myself, but I'll stick the DOI in the chat.
Thanks. Okay. And then okay. So if we then dig into the frequency trend, so we basically see a group of peak shows redshift, and the other three peaks shows blue shift. So normally the shift in this Raman bands could be due to the electron density change of corresponding vibrations. So, for example, increasing band length will give rise to a smaller frequency due to a smaller oscillator strength. And so that's our hypothesis. And from the previous literature, where they use DFT calculation to simulate what is the geometry relaxation upon the chemical doping, or when they form the radical anion. They first saw that, okay, the T2 unit doesn't have a really major effect from the doping. Instead, the bond length changes is dominated on the NDI flow D unit. And here the red bond represents the bond length is increasing upon doping, and blue is standing for decreasing. So if we look at their simulation, where, for example, the carbonyl bond shows red, so it has an increasing bond length. And if we look at our carbonyl frequency, we can see that after the plateau, when there is no reduction happening, there is actually a redshift of our carbonyl bond, which may indicate the increasing CO bond length, aligning with the simulation over here. And if we use the similar logic, we can see that these four bands also have redshift. So those are the CC stretch on NDI2 unit. They all show redshift, which may indicate increasing CC bond length. And these two peaks showing blue shift may indicating the CC stretch on T2 and NDI2 unit with a decreasing CC carbon bond length. And from the literature, I actually haven't found the peak assignment for these three peaks. So I think a more rigorous DFT simulation on the frequency shift or the bond length change upon chemical or electrical doping will be needed. Would be very helpful. So with that, let's move to the N2200 on ITO, but measured in non-aqueous solution. So so this experiment is done in sample nitrile, and we can see similar two reduction peaks. And from the potential dependent absorption spectra, we can also see what the previous literature reported for the two absorption peaks growth for monopolaron and the shoulder for bipolaron. We also use 515 nanometer Raman, which is more resonant with the polaron structure. So this is also the stacked Raman spectra scanned from 0 to -1.8. So we also saw similar features. For example, for the blue shaded area, those are the neutral N2200 peak. We can see that it decreases after the reduction of N2200 happened. Meanwhile, we can look at this 4 red shaded area, which is basically new features appears after or upon electrical doping. And these 4 area or bands are actually aligned with what the previous literature saw from chemical doping. So now the electrical doping and chemical doping shows similar trend in the vibrational information. We also did the ATR in situ ATR IR spectra of the N2200. So here we basically deposit N2200 on this silicon ATR crystal and do in situ ATR IR measurement under working condition. So here is the spectra showing the catalytic scan. So after -1.2 volts, we can see that there are growth. So this is also the difference absorption spectra. We can see that there are 2 new features growing after the N2200 reduction. These 2 new features actually aligns with what they saw in IR spectra upon chemical doping. And these 2 species are actually the carbonyl stretching, which actually vanishing, which is also aligned with what they observed. And the analytic scan actually shows the reversible trend. So till now, I hope I showed what we did for the in situ probing the monopolar and bipolar formation via these 3 kinds of techniques. And I think the major finding is the electrodoping actually shows similar vibrational feature change as the chemical doping does. And I think very interesting phenomenon that we observed for the potential dependent band area changes and also frequency shifts upon polyron formation needs more simulation and also experiment to understand. So future step, I will replicate the in situ Raman measurement of those vibrational information changes, and also collaborate with the activity calculation groups to help understand what is happening. So this is the summary for the first aspect of today's talk. So the second aspect of today's talk, I would like to introduce a current work where we use in situ surface enhanced Raman as a vibrational stock probe of the energetics at N2200 gold electrolyte interface. So this is our electrode configuration. We basically have N2200 spin coating on the ITO and deposit it with gold. And further, gold is functionalized with a benchmark vibrational stock shift probe molecule 4MBN, which has a nitrile over here as the electric field probe. And then deposit with sheen particles. So sheen stands for the shell isolated nanoparticle, which is basically used to enhance the 4MBN signal to be seen from Raman spectrum. So the 4MBN is a stark effect probe to measure the electric field and thus measure the gold Fermi level. So the motivation of this work is to understand the energetics of gold nanoparticles under N2200 working condition. So for example, this is our electrode and also solution configuration. So what when the N2200 is reduced, what is the energetics distribution in this kind of complicated system is a question that we want to answer. And also, we also want to understand the electron transfer mechanism from the N2200 to gold size. So basically gold here can be a mimic for example, platinum catalysts, which use the similar deposition method. But in that case, platinum is a catalyst for HER. It would be very helpful if we can understand what is the electron transfer from the N2200 to metal sites, for example, the catalyst. And another ambitious motivation would be it would be really difficult to do, but I was wondering if we can potentially provide using this method to study the electrical double layer structure at N2200 electrolyte interface. So this is our recipe for deposit gold and then functionalize with 4-MbN and then deposit with exchange. So before gold deposition, the current is very small, and after soaking the N2200 in the sodium tetrachloroaurate solution, and then apply potential at negative 0.2 volts in the KCl solution, we can see that there is a large reduction current which decreases with longer time. So basically, the integrated area here can represent how much gold can be deposited. However, we also really need to capture how large is the gold nanoparticle. So I think AFM, TEM, or XPS measurement on this gold deposited electrode will be really helpful for characterizing the size of the gold nanoparticle. But to my personal guess, it will be the size should be really small because this gold size cannot give us the proper resonance for our Raman spectra. So I think it is pretty small. So then the logic of using this method to measure gold Fermi level is as follows. So basically for this kind of metal electrode, the Fermi level of gold is readily known because we know how much potential that we apply to this system. So if we can measure the nitrile frequency as a function of Fermi level of gold, then we basically get a calibration correlation where if we know the frequency of nitrile in the similar environment in the solution, then we can actually calculate the Fermi level of gold. So this method is based on the Stark effect concept that I give a talk about a year ago. So basically, if we have the correlation between the Fermi level of gold and Fermi level and the nitrile frequency, we can use the nitrile frequency that we observed from the N2200 case to backtrack the exact energy of Fermi level of gold on N2200. It's a little complicated to say, but I think it will be clear when I show the data. So basically, for the calibration correlation experiment, I scanned the gold between 0 to negative 0.6 volts for 2 times of cathodic and anodic scan. And we can see that from the first cathodic scan, we can clearly see the nitrile frequency has a red shift, and then in the following anodic shift is blue shift back, and it's pretty repetitive. And then we can summarize, or after feeding, we can summarize the CN frequency change as a function of potential, and it shows like this. After averaging, we can get those information of frequency of nitrile as a function of Fermi level of gold. So basically it's indicated by this equation. And with that, we can move to characterize the Fermi level of gold over here on the N2200. So we did similar experiment. We apply potential from 0 to negative 1.4. And we can see the CN frequency, how CN frequency can change. So after feeding, we also summarize the nitrile frequency as a function of applied potential. We can see that before the reduction of N2200 happens, the nitrile frequency is not that dependent of the applied potential. Actually, this data is not that good, but we'll do more experiments about this. But after the reduction, we can see a solid shift of nitrile frequency. And so if you look at the red dots over here, which is the back anodic scan to prove that this trend is real. So we can see that there is, during the back anodic scan, there is also a shift and then plateau trend being observed. So then we can use the previous formula level gold and CN frequency calibration correlation to convert the nitrile frequency directly to the gold formula level. And we can see that the Fermi level of gold first stabilized at around -0.4, and after the N2200 can be reduced, the gold Fermi level shifts from -0.4 to -0.8. And we can so I listed the whole Raman spectra under the cathodic scan and anodic scan here. So basically, we during the experiment, we can capture the N2200 features and also Fry BN features together. So the dark green features stands for the N2200. We can clearly see that the N2200 starts to reduce in terms of intensity. And meanwhile, there is new features occur, which is attributed to the polyron formation. And the light color of green shows the Fry BN peak. So this is the CN frequency that we use to extract the Fermi level of gold. So to the right is a summary of what we observed, basically. So so the top panel indicates the neutral N2200 Raman amplitude. So after a certain point, it decreases. And for the second panel, this is the polyron-related peak, the new feature upon doping. We can see that after -0.6, there is a growing intensity in this polyron-related peak. Concurrent with the increase or appearance of the polyron peak, we saw the Fermi level of gold starts to shift. And I believe this is our major finding till now. And I will discuss about this more specifically later. And before that, I will show you another set of data that I use the same recipe. So basically repeat the experiments. If we just scan or apply potential at 0 and then directly to -1.3 and then back to 0, we can see that the nitrile frequency will first have a red shift and then blue shift and red shift. So I think the nitrile frequency is actually doing its work to record the electric field and is pretty replicable. So this is the summary of the second set of data. We can just look at the right figure where the Fermi level of gold actually has a pretty good plateau, and then after the reduction starts, the Fermi level of gold starts to shift. So I think what we saw is real. So for discussion, what we observe from this stock shift measurement is the Fermi level of gold will shift upon N2200 reduction or upon polyron formation. And it indicates to me that the electron starts to transfer from N2200 to gold only upon polyron formation. And I think the potential reason behind that could be before the polyron formation, because the N2200 will have a large resistance. So the applied potential will mainly drops inside N2200 or at the N2200 gold interface instead of at the gold solution interface. So basically there is a large area of electron transfer from N2200 to gold because of the large resistance. And from the observation of the Fermi level relation with the Polaron formation, we can see that if we just plot the Fermi level alignment among these four configurations, we can see that the N2200 Fermi level first change, but gold Fermi level wouldn't change. But at some point, after some point, the Fermi level gold will change with N2200 once it can get electron transfer from N2200 to gold. I think this is the main conclusion that we have right now, and we have more to explore. And for our interest, we really wonder a question, which is the N2200 solution interface a buried junction or an adaptive junction? So a buried junction just simply means that there is no ion permeable into the film, but the adaptive junction will allow the ion permeate or penetrate into the film. And I did some prediction to the energy level alignment in both cases. So if this if N2200 can work as a buried junction, I think this would be what's happening. So this solid line represents the Fermi level, and the upper lines represent the energy, the vacuum energy. So again, after the N2200 can be reduced, there will start to be potential drop at the gold solution interface. And before that, the potential will drop mainly at N2200 and gold interface because of the large resistance. But if the junction or the N2200 is ion permeable, totally ion permeable, pure permeable, that means the N2200 and solution will share the same E vacuum because we have the assumption that the counter ion can basically screen all the negative charges formed in the N2200, and this is what it will occur if we assume it is the adaptive junction. And we don't have an answer for this, but I personally think this energy level alignment may be a mix of both in the real case. And so in conclusion, I think the N2200 deposited with gold and functionalized with Tim Lian should be a good system to probe the Fermi level gold and further mimic the platinum catalyst electron transfer mechanism. And our big finding is that the Fermi level of gold on N2200 will start to shift during the formation of monopolaron. And we will continue doing this experiment and doing it in a more rigorous way. For example, study the cation concentration effect on the electric field generation. And thanks for listening, and I'm happy to take any questions.
Great job, Sa. I think there's a whole nother proposal in the chat while you were talking.
Okay.
It would be good that if we can capture that before we.
Yeah, I've asked Mike and Jen to do that.
Yeah. Thank you, Sa. That's a really wonderful presentation. You have done this a lot better than I could have done it. So I just want to bring up a point as we were discussing this, as Sa presented this. It really occurred to us that the polymer ITO interface look a lot like the nickel oxide, this porous oxide materials. So this is sort of way we're looking at it now in terms of its electrochemical and photoelectrochemical behaviors. This is something probably Annie will know a lot about, and so any comments and suggestions how we can proceed will be very much appreciated.
One thing I saw at the very end, and I'm just gonna react to what I saw at the end first, that's unique from solid state is that generally what's assumed in the solid state is that the organic gets pinned to the ITO and to the metal.
Yep.
And because it's such a low dielectric. And so what you've suggested is that the gold is actually pinned possibly to the organic, which is quite a unique phenomenon. And I think you'll see in the chat some conversations about from, you know, a hypothesis from Neil as well about the idea of, is it acting as a localized cation or a localized polarization point or a local nano environment that's ultimately giving you that result. One question I have is, do you think this effect would scale with gold nanoparticle size?
Yeah, that's a good question. I think if there is a gold film, the N2200 have to pin with the gold. So, but what we observe is the gold will shift with N2200. So I think there should be. It should depends on gold as size.
Wait, so is it a size, or is it really just whether you have a complete film that covers, or is it against a discrete island? I'm not sure. I guess I don't quite fully understand what you're thinking here, Sarah, in terms of the size.
I think these nanoparticles are so big that size may not matter. I mean, you got so many gold atoms, even in the smallest gold nanoparticles. What I would do is make the counter ion less important. Make it big and bulky and lower in concentration. My guess is the effect will go up, if that's true. It's also possible I don't know what I'm talking about. So,
well, and if we connect that back though to some of the early the conversation Andrew and I and everyone was having about, do you have to reduce the entire film to a radical anion before you can make the dianion? And if you truly have aggregates that are easier to reduce, and the gold is below or at the size of the aggregate, right, the rest of the film, the amorphous fraction may be there purely as spectator wasted volume, and everything is shooting through just the aggregate, which would explain why the gold appears to be pinned, because it's only interacting with a small fraction of the film population.
Yep.
So can you go to the slide where you show the UV vis spectrum before you subtract them?
Yeah. Here.
Yeah, so you can see the change is actually pretty small.
Small.
yeah.
So that indicate very small portion of the film is actually reduced.
And I would expect that to either be, again, this aggregate, or it would be maybe only the top couple nanometers of the film that are even being reduced. And I think that's a really important distinction, is it the only small volume that's able to interact with the solvent because it's hydrophobic, and so the water is not penetrating down into the film, or is it islands of faster charge carriers associated with aggregates, and the amorphous fraction in plane is just not participating? And that's an easy question to ask, and it's a really hard question to differentiate.
Tim, have you tried to do cross-sectional TEM of films like this? We can actually go look for the gold nanoparticles.
We have not, Sad, right? That's correct, right? We have not, and we're not really set up to do it here. But maybe if Natalie's online, I bet Georgia Tech can probably do that.
Georgia Tech has got some good capabilities.
If not, Alberto, I can't tell if Albert, I thought I saw Tyler earlier, but that would be a good question for Alberto, because Ariana's on here. maybe she can either speak to that or shoot her group a message and see if there's an opportunity there, because I know they've spent quite a lot of time doing the high-res TEM.
This is really exciting. So new, and it promises to be such a selective probe.
So there are really two things here, right? The first part really is first part of the talk, we really just want to get some spectral signature so that we can move on to do time result study. But this findings are already interesting. So with some help with the theoreticians, and maybe we could you know, provide some insight, publish a paper on just on this, the nature of this porons and biporons. So that's
Yeah,
one
Tim,
thing.
I would bet you that if you go down, take the KCl down to like millimolar concentrations instead of 0.1 molar, so it'll still support the electrochemistry. I'm betting that this effect will get bigger.
Mhm.
Because I think the gold nanoparticles will
Yeah.
play an even bigger role. Which would be
Yeah,
a
that's
really
a good
cool.
point. I'll try.
So remind me again, in the water, where to connect to the Stark shift measurement,
Mm-hmm.
you see very small changes in absorbance, but you do see all the way to the dianion.
Yes, we saw. So we didn't see the so let's see. So from the current data, we can see, okay, there are two reduction peak, and I think if we believe that literature is the dianion. But I don't know if we see any new features for dianion.
Just because the absorbance is so small, or the change is so small.
I'm not sure, because the change for monopolar is also small, but we can see them.
We don't have clear spectral signature of the dianion.
Dianion, yeah.
We see peaks that we know can be assigned to the neutral and anion.
I'm just trying to think of the picture I have in my head is if you only have 3 to 4 nanometer depth of the film participating in doping when interfaced with water.
You mean right next to the ITO? Is that a
No, I mean, so there's ITO film and there's water. So there's only 2-3 nanometers at the water N2200.
at the water interface? Okay. Mm-hmm.
So that to me, I think would rationalize why you see such a small absorbance change. My guess would be QCMD would support that you have almost no swelling whatsoever. And then what I'm wondering is if we can find a signature for dianion / bipolaron, what that's called to be determined, is does that suggest that you really have a bunch of charges piled up very locally, whether it's an aggregate or in that small fraction, versus charges being interdispersed throughout the film? And I don't know if I have an answer to that. Because like I said, it's easier to ask or pose or draw the picture than it is to go in and figure out how to do the measurement right at that small interface. Maybe we can talk more on Friday in our subgroup. Okay, it looks like we are out of time. Sa, thank you again for putting together. I appreciate the literature references as well to all of the different spectroscopic signatures you guys are trying to track. I think this gave everybody on the call a lot to think about. And then I believe in 2 weeks is the one Chad, your group is putting together? Along
Well,
with
it's,
my group?
I mean, I guess presentation is a good, what do I say? It should have been part of what we're trying to put together in 2 weeks. But yeah, so it's going to be multi groups talking about N2200 and some of the characteristics that have been defined already.
Okay.
Mostly Raman spectra, computed Raman spectra of Ni and di-Ni.
I don't know if that will be there because I think we're focusing on other things, but we can chat.
Okay.
Yeah. Trying to what the goal is for those that haven't been let's see, included on some of the emails, because we selected a small group of folks, is to try to kind of show how the center is working together on this material and the different routes that we can go, and how different aspects of some of the experiment and theory are coming together for better understanding. But I guess it sounds like too that we may need to be conscientious of time in 2 weeks, more so than normal. Is that correct, Aaron?
Oh, yes, because in 2 weeks we have the teal meeting update as well, don't we?
And
That starts at
actually, I
10:45.
think, yeah, we're going to have to end a little early, or some of us will have to step out.
Who is presenting on the teal meeting, Mike?
I sent out a request for volunteers last week, and so far, I've just gotten a few people saying they will be out of town or traveling. So we do not have. Wait, in 2 weeks? No, we don't have a presenter yet.
So folks, we need a highlight for 1 to 2 minutes of a success from the past 1 to 2 months. This can be verbal, although what we've done in the past is generally show publications. I'm wondering, given what's coming down the pipeline, the publication either needs to be published or submitted. I'm wondering if maybe we do either the molecular version of the N2200 study or the ChemCom paper maybe might be a good one as well. It's just a quick little 1-2 minute.
Both Seth and I are out of town at another EFRC annual meeting in that day.
But since it's only 1-2 minutes, either I can do it or maybe Annie would be willing. I'm thinking, or it just needs to be a co-author. So the other one we could do is have Abhishek do it if he's interested.
He's in India for
a
really long period of time.
Yeah, he's in India for a month.
Yeah.
Do you want to then just say, Aaron, you'll present on the chemical communication paper, or we can ask Annie to do it?
Yeah, I would say if we could get the highlight slide made in the next week, then let's do the ChemCom one since it's.
All right, I can make a slide. Is there any constraint format wise or anything?
Yes, yeah, it's a prescribed Dewey template of.
Okay.
I'll send you the slide.
All right, thanks. Yeah, I mean, I'll
maybe send him a couple
somewhere.
examples too, Mike, just so he can see what it looks
Great,
like.
thanks. Yeah.
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 Okay.
All right. Yeah, I have to leave, I'm afraid now, so I've got.
All right, I need to jump off. Thank you, everybody, and thank you, Saw.
Yep, thanks.